stop the sharing.
She's Mariana Carrillo González from Imperial College in London. And she will give us an introduction to the double copy and its application. And this is the title of her first talk today. Please, Mariana.
Yes, I'm going to try to share screen.
Yeah.
Let's see. Okay, can you see that?
Yes.
Perfect. And okay, so thanks for the invitation. I'm really glad to be giving these talks. So indeed, I'm going to tell you about the double copy and first explain what the double copy is and this different kind of duality, probably not the one you're all used to, and also some applications that have recently been developed that are new and has led to a lot of new research in this past probably 5 years. Just because at the beginning, this was only a relationship for scattering amplitudes, but now it is broader. It can be for correlators, it can be for classical solutions. So we're going to review this. So the first lecture is basically just introducing what the double copy is. And in its more famous version, which is the Yang-Mills squared equals gravity. So I'll explain why or how you can square Yang-Mills to obtain gravity. Then I'll show you two different types of building this double copy. One of them, it's called the KLT double copy, and it has stringy origins, which is basically how all of these relations were found at the beginning a while ago. And later on, it's the color kinematics duality, the so-called BCJ double copy from Berg, Carrasco, and Johansson. And this actually explains in a deeper way why we can square kinematics and actually find gravity. And at the end, I'll just show you that there's actually more than just Yang-Mills and gravity. There's a whole relationship of theories that you can find with this double copy. And also you can find classical solutions. But, and here are some references in case you want to take a look at it. For the second lecture, we're going to focus on new explorations, and we'll see how those things go. And we can pick certain of these depending how fast or not we go. So let me start with what's going to be the goal for these lectures. And the idea of the double copy and many dualities that you find with gravity is that through gravitational computations in general, it's really hard for us to understand quantum gravity, to even do calculations sometimes in gravity for scattering amplitudes. In this case, it's really hard just from the structure of our Lagrangian and what the vertices you have. So we would like to find a simpler way to do this. And as you have seen in different cases, the use of dualities is always a fruitful approach on finding easier theories that actually give you some gravitational observations. And in this case, the simpler theory will be Yang-Mills. So let's start and look at the simplest cases. And it's just the S matrix in flat space. And for gravity, as you know, you just grab your Einstein-Hilbert Lagrangian, do an expansion around flat space, and then you try to construct all the vertices that you have, just a standard QFT. And what you will see is that instead of having just a finite number of vertices, you have an infinite number of vertices. So you have a 3-point, a 4-point, and so on, which already starts making things harder because if you want to compute higher point amplitudes, you have a lot of vertices to use. And furthermore, if you even just look at the 3-point vertex and what's its expression, which I'm writing here in a very compact way, if you actually expand these are just momenta and just contracted in different ways. And these are permutations that you will need of these 3 legs, which is a notation that you don't really need to care about.
I'm sorry, Mariana, one second. Yes? I'm stuck. Yeah, I think we're all stuck in the first piece of your definition.
Okay, you should. Okay, that's bad. Let's restart this. Thank you for telling me.
No, it's okay.
I guess the credit goes to me. So.
Okay, let's see. Let me restart screen sharing. Oops. Okay. Sorry about that. Now I'm having issues with sharing the iPad. So let me restart the app. real quick. And so I guess recap of what I was saying, you weren't seeing anything. Yeah, these were the references for here. This was the idea for what we're gonna do maybe for the next lecture. And well, if you weren't seeing this before, here are the vertices for gravity that you usually use to compute your scattering amplitudes. And now that you actually can see the expression for your scattering amplitude here. So this will be the 3-point vertex. And here is the notation I was talking about. And if you actually expand this, that you will just have a lot of terms of momenta dotted in different ways of these 3 external gravitons, you're going to end up with about 100 terms, which of course, doing it computationally now with Mathematica, it's easy, but we would like to have an easier way of computing the S matrix of gravity. And now we go to Young-Mills. And if you just want to compare how simple it is, in Young-Mills, we know you have a 3-point vertex, a 4-point vertex. The 3-point vertex has this very simple expression in terms of momentum. And just to highlight here, I'm going to put in blue always what's kinematics, in red what's the color factors, and the coupling strengths here are in green. So the idea is how can you even relate something that looks like this to the big mess in gravity? And the solution, which was actually noticed 100 years ago, basically, is that you need to put it on shell. So instead of just looking at the vertex, if you look at the scattering amplitude on shell, and you remove this color factor and square the kinematics, then what you will find is that you obtain the scattering amplitude of gravity. So basically you have the following relationship on shell. And this has been realized for the 3-point amplitude a while ago. Now, I'm calling these color strip amplitudes with this notation of 1, 2, 3. And it's probably something that not everyone is used to. So I'm just going to do a short review on what this notation for color strip amplitudes are now. So
why the term color stripped?
So the idea is that, for example, here, you will remove this factor completely. And
okay.
that will be your A3, 1, 2, 3.
Thanks.
Sure. Yeah, and please interrupt me anytime. It's yes, there's another question.
Yeah, so this is for any Young-Mills theory? Or
sorry, what's that again?
Is this for any Young-Mills theory?
So it's gonna go for UN or SUN too, but any N. Yes.
It's independent of N, let's say.
It's independent of N, but if you have another group, then you, well, I really need that you can write all the amplitudes as single traces. And otherwise, then some of the things don't work. So let's think of UN as the most general case. Yeah. I think there's another question by Andres.
No.
No, it's just the hand is still.
Oh, okay. Okay, so yeah, short review of what color order amplitudes or partial amplitudes are. And the idea is, in Young-Mills, basically, you can write your amplitude in this shape. I'm just gonna put outside the coupling strength. Then these have different names, color strip, color order, or partial amplitudes. And you have this special ordering here because they correspond to the factor that goes with the trace of the generators of your group. That again can be UN or SUN. And here is a sum over all the permutations over the legs from 2 to n. So you just fixed one of them. So you basically have a basis that's n-1 factorial. And the reason is because these traces are related to cyclicity. So there's a lot of these terms that will be redundant if you actually didn't fix one of the particles here. So that's why you just fix one and then you do permutations over the other ones to not have redundancies. And this basis is called the trace basis for your color order amplitudes. And for example, if you want to compute a 4-point amplitude like this one in this order 1, 2, 3, 4, so this will correspond to your trace of like TA1, TA2, TA3, TA4. So what you would do is just look at the following Feynman graphs with this special ordering of the legs. So this is like a 1, 2, 3, 4. And here you again has 1, 2, 3, 4. And this is what we call your channel because it's going to give you a P14 in here. And you can also have contact terms. So you got to be careful to include all of those in here. So these Young amplitudes, they don't only satisfy these simple relations due to cyclicity, they have extra relationships, and these are very important for the double copy. So let's start first with the simplest one. So these are called Claise-Cloyd relations, usually just called KK. And they actually tell you that instead of an n-1 factorial basis, you have an n-2 factorial basis, and this will be the KK basis. And the reason why you have this smaller basis is because we have all of our fields are in the adjoint representation here. And since they're in the adjoint, you can always have this relationship between the structure constants and the traces of the generators. But besides this relation, we know that these structure constants satisfy Jacobsi relationships. So this gives you further relations between your traces. And if then you look back at your amplitude that you have here, well, then there's further relationships between these partial amplitudes that come when you have adjoint particles. So you're going to have these extra relationships that, for example, here I'm showing what the 4-point amplitude looks like. And it's just relating how different orderings of your color actually relate to each other, which in this case is very simple. For 4-point amplitudes, also, this is called U1 decoupling. And it's called U1 decoupling because you can also infer it if you have one of these generators and set it to be the U1 generator. And then you will find a lot of relationships between those traces too. So far we have two bases, which we can write our amplitudes in. So the trace one that I showed you before, and this called KK basis that it's usually written in terms of these structure constants. Now, there's one more set of relationships that these Yang-Mills amplitudes satisfy. And I'm not going to show them immediately. It's just a teaser. So they're going to be n-3 factorial independent ones. And this BCJ, so from Bernd, Carrasco, and Johansson, so you can imagine it's related to the double copy. And it will be related to color kinematics duality. And we'll see an example of how having explicit color kinematics duality leads to these extra BCJ relations. But for now, just know that there's more, and they reduce the number of independent amplitudes. So if there are no questions on that, I will move on to the next part. Okay. Because we're actually gonna see now what the double copy is. Now that we know what our colored order amplitudes look like and that they can be in different bases, let's just think of them for most of the time in the trace basis. So we're gonna have objects like this. And these extra BCJ relations actually appear in a very neat way in string theory. So these probably were the first things that were noticed. But the nicest explanation is that they're actually monodromy relations for the string amplitudes. So for the string amplitudes, you basically, for the open string, you have an interval over the disk, and you have integrations that if you fit 3 of the points into disk, then your SL2C symmetry. So say you have a 4-point amplitude and 3 of those are fixed and at usual 0, 1, infinity in the Z plane. Then you're gonna have that your amplitude is gonna have a lot of integrals with terms of BZ and I guess I didn't put in the factors. Well, CIs and CAs. Sorry, I don't have enough space here. But just imagine there's a function of polynomials of C's in here. But this can be integrated at different contours. And depending on your color ordering, this contour is going to look different in the Z plane. So the idea basically, and I'm not gonna go into detail in this one, but the idea is that if you change your contour of integrations and use monodromy relations, you're gonna find that there are extra relationships between these color order amplitudes, just out of the structure in the disk for the open strings, which is very neat. And there's a nice proof in this paper if you wanna look at it. And surprisingly, this tells you that the number of independent one is n minus 3 factorial, just like the case in Young-Mills. But this is for the open strings. And the example of this relationship for the 4-point open string amplitude looks the following way, where alpha prime is the usual string parameter. So for the sake of this talk, I'm just gonna work usually in the field theory limit. So let's just take alpha prime goes to 0 here, or the tension going to infinity. And you find this nice relationship between 4-point amplitudes, where here TNS are just the standard Mandelstam variables. And yeah, this is like the first example of this extra relationship. And when you say, okay, it comes from the low energy limit of string theory, it's not very clear. Why should it hold for field theory? It's probably just an accident. It's probably only something that holds in string theory, but we'll see later that this is actually more broad.
Sorry, Mariana.
Yes.
So essentially, you are looking at crossing symmetry in a low energy limit or something like that.
For this simple case, it looks something like that. But when you go to higher points, it's a little bit more complicated. It's not really crossing symmetry because, I mean, actually in the strings, the monodromy relations, actually, you have to change your integration contours to make relationships with each other. So I know it looks like crossing symmetry because it looks like you're changing T channel for S channel here.
Mm-hmm.
But the higher points is more complicated.
Okay, great, thank you.
Is there another question?
Yeah.
Mariana, if you keep one next order in alpha prime, not the purely field theory limit, but the next one,
yeah,
what happens with this? Is there anything interesting going on, or how it goes?
Yeah, so what we do when we keep the next order in alpha prime is like think of it as higher derivative corrections to the theories. And it's complicated because these simple relationships, like the BCJ field theory relationships, do not hold order by order in alpha prime. There's actually issues. The monodromy relations give you something different order by order in alpha prime for certain terms, but then there's certain higher derivative corrections if you want of Young-Mills and gravity that still satisfy the standard BCJ, but there's other that just don't. So it's actually another field of study, like active research of trying to understand what are the correct higher derivative corrections, and string theory tells you from the alpha prime expansion which ones can and which ones cannot. Yeah, so the fact that you have these extra relationships actually led people to think there could be something else. And a while ago, again, in the 86, actually, it was formulated that by KLT, Kawai, and Tai, that at 3 level, the closed string amplitudes can be equal to the square of the 3 level open string amplitudes, which in some sense could be intuitive, but there's a nice formal proof. And again, since here we're just gonna go to the field theory limit, what this implies is gravity equals Young-Mills square. And I'm gonna explain exactly what this square is in a second. And this square usually refers to a KLT double copy if I ever write it this way. But gravity, I mean, we're saying this is the low energy limit of string theory. So it's not only your graviton, we have a Coll-Ramond field and we have a dilaton. So just so you understand, well, intuitively why you want this, if you go to d equals 4 and you check your degrees of freedom, you go and you grab your graviton, you have 2 degrees of freedom. Here, your 2-form field is going to be dual to an axion in 4D, so it's just 1 degree of freedom. And your dilaton is going to give you another degree of freedom. So you have 4. On the other hand, for Yang-Mills, in the equals 4, you have 2. So 2 times 2, you have 4 degrees of freedom. So the degrees of freedom matching, usually you expect this matching of degrees of freedom when you square something and what you're gonna get in your double copy. So this it's nothing formal, but it's some way of having a clue later on if you wanna wrap different theories on these sides and knowing how many degrees of freedom you're gonna get. And of course, if you put the degrees of freedom for an arbitrary B, this is gonna match nicely.
But what happened with the n here? Because Yang-Mills has 2 times n minus 1 degrees of freedom.
With the what? Sorry, I didn't hear that.
But SUN Yang-Mills theory has 2 times n minus 1 degrees of freedom.
Well, I'm counting degrees of freedom of the particle, like a mu. Not every a mu A as a degree of freedom, but a mu itself as a spin 1 particle.
Okay, you counting like it's a photon.
Yes, because okay, so maybe that's not clear, but let me write a trivial example. If you write, yeah, let's make it a little less trivial. So let's write it like this. So let's say you can write your field like that. When you do the double copy, what you do is to strip the color. And what you double copy is just the kinematics. So in some sense, you just want the square of the degrees of freedom in the kinematics part. That's why.
Okay, thank you.
Sure.
Mariana, may I ask another one that maybe is the same question that Andres just asked, but dressed differently, maybe. And it's a question that I'm a bit uncomfortable asking because it's about local symmetries. On gravity, you have diffeomorphisms. In Yang-Mills, you have, okay, you may say gauge transformations.
Yes.
How do we create the diffeomorphisms from the gauge transformation or vice versa?
So in the scattering amplitudes way, we're actually, once I reach the explicit example, I'll explain why. At the linearized level, you get actually from gauge transformations, you go to diffeomorphisms. So yeah, I'll come back to that in a bit. But yeah, let me just leave it for later. Okay, so just so you can see the actual action I'm talking about here for gravity, this is it. This will be the low energy limit of string theory with our usual Einstein-Hilbert, our d-electron field, and the field strength for the Calvert. So the explicit now relations that I've been talking about in that squaring at 3 points, as I showed you before, it was simply like an M3 is equal to 8-3 squared. It's trivial. At 4 points, it starts to get a little less trivial, and you have a Mandelstam variable S here and 2 different color orderings of the Yang-Mills field. And this will give you gravity. At n points, this is the formula, which is slightly more complicated. So let me just go piece by piece here. So here I have an index left and right, because you can actually put different theories on each side in general in the double copy, even though right now I'm just talking about Yang-Mills square. Now here, you again have one of the particle sticks, 1 and the sigma. Now you're gonna do a sum over n minus 3 permutations, and then you have the nth ones actually fixed. Now here you have something that we call the KLT kernel. And this is basically just a rational function of Mandelstam variables. We'll see explicit examples later. But the idea basically is that, surprisingly, if you multiply 2 Yang-Mills amplitudes, this kernel will compensate appropriately to give you the correct poles and the correct residues that you want for gravity. I mean, it's completely non-trivial because you have simple poles here multiplying other simple poles here, and there's just no reason why you're gonna get the correct poles in the other side. So one thing that you really want to look at all the time with scattering amplitudes is just that you have the correct poles, they're simple poles, and the correct residues. You know what you want in your theory when you know what's the particle content. So we'll see examples explicitly of what this KLT kernel is later, but it basically what it does is to compensate exactly in the right way to give you the correct poles and residues that you want for a spin to particle by multiplying two spin one particle amplitudes. So we reached the question of why removing color, meaning why taking the color ordered amplitudes and squaring them gives you gravity. Like there, so far, I mean, okay, there's a stringy origin, that's good enough, but we would like to have a better explanation. And to do that, we're gonna go to the new version of the double copy, which is the so-called BCJ double copy. So since I'm changing to a different style of double copy, let me ask if there are any questions before I move on to that. Okay. So then I'll start with the BCJ double copy and the so-called color kinematics duality. So instead of using the partial amplitudes in these trace spaces that we've been using and stripping color from them and squaring them, now we're gonna write first the whole amplitude here in this way. So here is gonna be a sum over trivalent graphs, which I'll explain in a second. These NIs are called kinematic factors, and they're basically just functions of momentum polarization vectors. These CIs are color factors, so depending on the basis that you want to write your amplitude in, it can be functions of structure constants or the generators. For example, in the KK Cleese-Clough basis that I had before, this partial amplitude will just be a sum over some of these n's over these pi's that are the propagators with difference. Some of them are 0, some plus or minus 1. And again, if this is too abstract, at the end I'll show an example. And these propagators are just like, yeah, the propagators of your amplitude. So it will be the Mandelstam variable. This will be just like an S or T. So now let's actually explain a little bit more about this formula. So first thing is, what do I mean by trivalent graphs? So I just mean the following. Every cubic vertex that you can write explicitly, that's a trivalent graph. So this will be the S channel, P channel, U channel. And higher points, you will just have as many of this style as you want. And the number of graphs actually grows largely with n. So we have 2n minus 5 double factorial graphs for an endpoint amplitude. And you will say, okay, this looks like all of them have poles. But as I said at the beginning, we know there's contact terms like this. And the way you write those is by making them look like pole terms. So you just can graph one of these contact terms and multiply it by a 1 of S over S. And now you can say this is a sort of trivalent graph in this way. And then this will have a contribution over here now in one of these NIs by something like your P4, your contact term, times an S. But also that tells you that you can just put that contact term wherever you want. You can put it on the S channel, on the T channel, the U channel, you can put it symmetric, which takes us to the fact that these ends are not unique. And in fact, the way that you can shift those ends and keep the amplitude the same is called a generalized gauge transformation. So keeping our amplitude invariant, we can change these ends in the following way. If you just like go back and plug this over here, you will find that this indeed keeps the amplitude invariant because of some properties of the color factors that I'll mention in a second. And these kind of shifts are actually, if you just want to look at what happens in the action in the Lagrangian with them, they correspond to gauge transformations, which is expected, but also field redefinitions. So it's a combination of both when you do these kind of shifts. So now let's go to see what color kinematics duality is. So I said that there's some special features of the color factors. And these are the algebra that, of course, follows for UN in this case. And here we have Jacobsi relationships and antisymmetric relationships. So I'm using this kind of a notation of the color factors again with the C's, but you can just imagine, as you all know, these are like a structure constants, and they could be like C, D, E, and this could be the CS channel. Now, this notation that I'm using for ABC, so it's, as you can see here, for the external leg, so this will be like the 1, 2, 3. So if I have ABC, this will be S channel. Then if I switch it to BCA, like in here, this will be the T channel. And if I switch now here, CABC, this will be the U channel. So these are like the labelings of the external legs here. Okay, so you have Jacobi, and I made it complicated like this because 4 points is obvious that is ST and U, but if you have N points, you're gonna have more legs. So you're required to actually label 3 of them. And antisymmetry, just standard antisymmetry of that appears in structure constants. The big realization of Bernd, Carrasco, and Johansson is that this algebra that just naturally appears in Yang-Mills also appears in its kinematic sector. And by that, I mean in these kinematic factors that I just defined in the scattering amplitude, they can actually satisfy the same algebra. And this is for Yang-Mills, and it's very special. So not any theory can satisfy that. So another big question in the community is which theories can satisfy this? And this is still an active research because there are many, and they satisfy it in different and non-trivial ways. So let's look a little bit more of exactly what these Jacobsi relationships are. So as I said, this S channel, again, you do it with this A, B, and C color ordering. B channel, again, here I'm keeping the ABCD the same, but of course I changed the legs, so this is a little different. RU is usually crossing the legs, but for endpoints, this is gonna be particles that are inserted in your graphs. So you can have many more Jacobsi relationships. For example, at 4 points, you only have 1. And if you go to 5 points, all the different like 4 point sub-amplitudes that you can find in your graph are gonna give you a new Jacobsi relationship. So for 5 points, you have 9 Jacobsi relationships. And of course, this grows more and more. But the fact that this kind of relationships not only holds for color, but also for kinematics, gave the idea that now we can exchange in that amplitude the C's for the N's in the same kind of idea of the KLT. And we're gonna write this as our double copy proposal for the scattering amplitude. So basically what I did was just the Yang-Mills was N C over D. Just literally remove the C, put an N, and see what happens. Magically, again, you get the right pulse, you get the right residues, and you get the scattering amplitude of gravity. At least this time, you can say you have a reason for it because you have the same algebra for both the color and kinematic parts. So, and again, here I put a tilde because you can match different left and right theories. So,
sorry, can I interrupt?
Yeah, please.
So the way that you phrase that means that that's not the reason. Like that's not the fundamental reason, that because they have the same algebra, then they have the same like poles and the same residues.
Because they have the same algebra, you can exchange the color for the kinematics in this expression. And at the end, because they have the same algebra, it's actually what's going to tell us that this gives rise to the correct poles. I think it's going to be more clear in the example. The thing is, there's different little pieces so for the double copy. So one is having color kinematics duality in the sense of having this algebra for the scattering amplitudes. The other one is having the BCJ relations that I showed before, and those two are actually equivalent for, at least for a theory in the adjoint representation. And in those cases, those two things help you find that this gives you the correct pose. If you don't have those things, people have built examples and they have shown that they don't. There's not a direct proof that like any theory that has that is going to give you something with the right pose. But I mean, we all seen examples that you need it.
I see, thanks.
Okay, are there any more questions? Because I'll move on to something slightly different. Okay.
Mariana,
yes.
Sorry. When you are talking about the amplitude from the gravity sector, you say that you are calculating vertices from the graviton.
Yes.
But you say also that you have other vertices from the gravity side that come from dilatons and the AMU sector. And these sectors don't have anything to do with these dualities in double copy.
Oh, every time I say that double copies to gravity, it's always including gravitons and dilatons and two-form fields. When it's 3-level, and if you just look at 4 points, then yeah, it just gives you the scattering of gravitons. It depends on this external polarizations that you're gonna pick on this side. So at the end, there's also like a relationship for the polarizations, if you want, that would look like that. So depending on what you pick here, you're gonna extract on the other side. So if you pick them symmetric, you're gonna extract the graviton part. If you pick the trace part, you're gonna extract the dilaton part. If you pick the antisymmetric part of the polarizations, you're gonna extract the two-form field. So you get everything. You get the full low energy limit, but it depends which polarizations you pick here. And it basically depends on which kind of processes you're looking at for the scattering amplitude.
Okay, thank you.
So yeah, the duality, when I say, every time I refer to gravity now, it's always the full package. And the duality, yes, it holds for the whole thing. Probably another important thing to mention is that so far what I showed was the KLT double copy at 3-level, and this is also the expression for 3-level amplitudes, but you can actually do the same for loop amplitudes. And it's just gonna be inside the integrand. So you're gonna have integrand over how many loop you have, and you're gonna have another expression of the following way. And just inside the integrand, you're gonna be able to do the same kind of replacements. But here I'm just gonna show 3-level. So just so it's clear that it's the whole theory, not just a magical accident of 3-level. Okay, so I'm gonna, actually I'm gonna show the explicit example for Yang-Mills to gravity. So for the 4-point. So actually expanding that expression that I showed before, now for the 4-point is just S channel, P channel, and U channel contributions. And here I'm gonna show you explicitly what that color factor looks like for Yang-Mills. Again, this could be just UN. So here I'm using the KK basis. So I'm working with structure constants. And this CS is just defined in terms of the structure constants in this way. Sector factor of 2 is just, so you can actually just have a G square over here, and NS is defined in a nicer way. But these Fs, you know that they satisfy Jacobsi relationships. That's just the standard thing. And now the NS, we have the following expression, which It's a lot of algebra, but it does satisfy the same Jacobis and antisymmetric relations as the color factors. And you actually have this part which corresponds to the pole terms, and then you have an extra part that, as I said, you have to write the contact term as if it was a pole term. So it just has this extra S over here. And this is a specific choice of, as I said, these ends can be shifted in a special way. And I think it's not going to be obvious at all to anyone in a lecture here because you cannot do the algebra. But if you can just replace them like that, you will see that that's actually the scattering amplitude for gravity. And as I said, depending on how you pick the polarization vectors, you're going to get the contributions on the other side for gravity. And we'll actually see a special example where you could actually just square them like live and see that this works. Because I think if you don't really work it out in front of you and see that it works, sounds like magic.
I'm sorry. Can I make you a question?
Yeah.
Yeah, just one little thing that you said, that you can choose different, the NS are not unique. And then you just said that there is a particular choice in which the left-hand side matches gravity, or I listen wrong. You said something about that.
Sorry, I meant there's a particular choice for the polarization vectors.
Oh, okay.
So it's what I was mentioning, that you're gonna assume that your polarization tensors in gravity are just formed out of the polarization vectors in Young-Mills.
Okay.
So depending which polarization vectors in Young-Mills you pick, if you pick a symmetric combination, because you have plus and minus, right? Okay. So depending if you pick a symmetric combination, you get the graviton contribution. If you get antisymmetric, you get the two-form contribution.
Okay, thanks. But I can reshuffle my NS, my NT, and everything, and you should get the same. Okay, thanks.
Yeah, you can reshuffle them in this way. Any function there, and that will be an S in this case. Same for T and U.
Thanks.
So sure, no problem. Yeah, the reshuffling always has to keep the Young-Mills amplitude invariant, and that's it. Okay, so this is it for the BCJ double copy, but there's something more that you can realize now that you have it, like now that you express it in this way, where you have the color kinematics algebra. There's I think a sort of obvious question. It's like, here I'm exchanging color for kinematics, but I can also exchange kinematics for color. So let's do that. And instead of grabbing your amplitude and putting two N's, you grab your amplitude and put two C's. And you get a scalar field theory. Because basically the idea, the higher you go into double copy, you're kind of going to higher spins. You remove kinematics and go with colors, and you lower the spin. So now you have a spin zero theory. Now, given the structure of the double copy, this has cubic interactions. And this is called the bi-adjoint scalar theory. It has two color indices in the adjoint that again can be from two different color groups. So that's why, again, I put a tilde here. And in principle, one could say, oh, what's interesting about this theory? It's a phi cube, it's not even well defined. It has two adjoint indices. But surprisingly, it's one of the most fundamental things for the double copy. So what we have is that the Lagrangian, this interaction term, the cubic one, it looks like this. It's with two structure constants. And the big surprise is that this is how we relate BCJ and KLT. In KLT kernel, I told you there was a KLT kernel that surprisingly gives you the right poles when you square the amplitudes to get the gravity. Here, we have seen that there's this weird phi cube theory that appears. Well, these two are actually related, and that KLT kernel that I called before Sn is actually just the inverse of the scattering amplitudes of this scalar field theory. So this scalar field theory is sort of like a identity operator, if you want, in the double copy. So for KLT, we were writing scattering amplitudes like oh, with an SN, I'm denoting SN like this, and this was giving you gravity. If you switch one of these amplitudes, I told you I can pick whatever I want. This is Young-Mills. And if I could here my phi cube, this is the inverse of phi cube, so they cancel. And what you're gonna get here is Young-Mills. So this phi cube is sort of an identity operator for the double copy. No matter, given that in the KLT it appears as the inverse, no matter what you want to double copy with, it will always give you the same scattering amplitudes.
Sorry, Mariana, just about 5 minutes left, okay?
Sure. Yeah, that's perfect. Then we'll give the example review tomorrow. So what we have so far is that if you start with Young-Mills, and now that you have color kinematics duality, exchanging color for kinematics gets you gravity. Exchanging kinematics to color gives you this bi-adjoint theory that's actually giving you the KLT kernel. And probably an important comment here is that this KLT kernel be given by this bi-adjoint theory is not the only option. Here, there's a paper that was shown by Nicera in 2016 that there's also a generalization for a KLT kernel with a different scalar field theory for this string theory case. So this is like the stringy KLT kernel. And actually this year, probably like a month ago, there was another paper where they showed that there are higher derivative corrections to this theory that will also give you a reasonable double copy. So there's still a quest of understanding what's this kernel and what's like this unity operator in the double copy that can give you the most general version of a double copy. So let me tell you that as we've seen so far, just gravity and Young-Mills and even this bi-adjoint scalar are not the only thing we have. There's actually this broader web of relationships between a lot of theories. And here I'm just showing some cases. Here, there are different ends that you can have, for example, for a nonlinear sigma model. This nonlinear sigma model is from a UN cross UN to the diagonal UN. And this will give you different kind of kinematic factors. Of course, now for a scalar, you can play the same game and you get some higher derivative scalar field theory that has a lot of interesting properties. You can play the game of interchanging these kinematic factors with the Young-Mills ones. You get Born-Enfeld. There's many games you can play. There's many more theories that you can also include here. And yeah, it's way broader than we expected. So if we only had this, we could say this just comes from string theory and that's it. But we have many other theories and we have many other ways of doing replacements between exchanging color and kinematics and just playing with your amplitudes. So there's a quest of understanding what's the most general way you can do this. And just let me mention, you can also do this for loops, as I said, adding supersymmetry for particles, including in the fundamental representation, because so far I just talked about a join. For massive gauge bosons, it's tricky and it's ongoing research. And more interestingly, you can also do classical solutions and curved spacetimes. So next lecture, we're gonna go to these cases and maybe a short review of what we did here. Yeah, let me just not do the review, but maybe I need to answer Carlos' questions because I didn't reach that part. So let me just finish here.
Okay, great. So let's thank Mariana for her talk. We have 10 more minutes for questions and then 10 minutes break. Okay, any question?